Okay, so we have green boundaries, and then in materials, quite often we are dealing with many phenomena that involves the so-called migration or movement or motion of the green boundaries. So let's try to understand from energy perspective what drives and how does the driving force would move the green boundary. Okay, so as we said, we always start from energy. Green boundaries are so-called high energy regions with excess energy. Access to what? To the bulk, assuming perfect without green boundary, within when the material are within the inside of the green. Okay, and a lot of things such as annealing, a lot of processing such as annealing, when you heat it up, heat the material up, they would cause the rearrangement of atoms. Okay, and as a result of the rearrangement of the atoms, the green boundary quite often may move, as you would observe when a polycrystalline material, when you heat it up, typically the green, if you start with small, they would grow. When green grows, what happens to the green boundary? The green boundary has to move, right? So that's fundamentally okay. We are going to deal with the motion of the green boundary, and fundamentally speaking, the interface in this case, green boundary motion, fundamentally is driven by the atoms moving from high energy state to a low energy state. Or if I have it here, what I'm plotting roughly, and vertical axis would be gives free energy. Horizontal, I'm just roughly using location. I'm plotting from two greens, okay? Two greens, green 1, green 2, and then roughly, okay, I have these types of curve from green 1 to green 2. But based on this plot, again, this is only a schematic and not a precise description. From this one, which green has higher energy? Well, green 1 is higher energy, right? Green 2 is lower energy. And if, what is this peak here? This we call delta GA from this one valley to the top. This is what we call activation energy for the atoms to move from one green, green 1, to green 2, right? Going one way. Okay, let's say we have enough kinetic energy. The atom, some of the atom would have the kinetic energy enough to overcome this barrier. Then that atom would move what? From high energy state naturally to low energy state, from green 1 to green 2, right? That's typical. That's the typical case, so-called the spontaneous case. Okay, all from geometry point of view. I still have green 1 on the left, green 2 on the left, on the right. Okay, and when the atoms move from green 1 to green 2, do you see it's actually as if the green boundary is moving backward, right? The green boundary motion is actually backward. Makes sense? It's the green 2 is getting larger, while green 1 is getting smaller. The motion is this one. Okay, now let's think of the energetics aspect of this one. If we define a few terms, what is delta x? The distance, the displacement of my green boundary due to this motion, whatever. And the delta g, what is delta g? We kind of define it as the so-called difference in volume free energy in green 1 versus green 2, delta g. Okay, the difference per volume. Okay, free energy per free energy. Make sense? And then Vm, if we define Vm as our molar volume, what does molar volume mean? How much volume, how much cubic meter or centimeter cube per mole? That's so-called molar volume. Okay, and as a result, the molar free energy change associated with the movement of delta x of green boundary for unit area. If I ask only unit area, I'm only considering unit area of this green boundary. The molar free energy change, I write it as this one. Delta G, okay, how much energy per mole times the total volume divided by the molar volume. The volume divided by molar volume gives you the how many mole times delta G. Actually, I made a mistake. It should be volume free energy. Okay? So that's the free energy change if we think of the difference in energy. But because it's a motion of what? Green boundary, right? In this case, atoms move, but in what we observe is green boundary moves. If we think of F is the driving force for the green boundary motion per unit area, the force per unit area, okay? Then the work done in this process. Remember, we said, okay, for the green boundary to move from the original location to the new location, let's say F is my driving force per unit area. Then the total work is what? Force times displacement, right? And this force is per unit area. Then I have to time this one for my unit area. Then times delta x is my displacement. This is my total so-called work. Force times displacement. Force is force per area times 1 for unit area. Okay, so this is my total work. Total work from energy conservation point of view of thermodynamic first law, total work would be equal to the internal of free energy change, right? So that's how we are going to write it. The work would be equal to delta G times delta X divided by Vm. And of course, in this case, the delta X and the delta X would cancel each other. And as a result, the so-called fundamental driving force for what? Driving force for the motion of green boundary would just be delta G over Vm. Again, what is delta G? Delta G is, I have a mistake here. It should be the difference in molar free energy for between green 1 and green 2. Between the two green you are considering. The difference in molar free energy divided by the molar volume. And of course, when delta G equals 0 means what? When delta G is 0 means my two green have the same molar free energy. And naturally, in that case, my green boundary, of course, would not move. Make sense? That's just how you understand it. Okay? And then, in this case, the delta G has the unit of joule per mole. And joule per mole. And the V would have the unit of meter to the power of cube per mole. Okay?